Okay, now we start talking about, before describing the notion of NP complete, we already saw NP. Let me remove this thing. We already defined NP. Now we're going to study the notion of NP complete. Yeah. Where a problem is NP complete. For that, we need to talk about polynomial time reduction. So a language, remember the language are the problems here. So a language L1, is said to be polynomial time reducible to another language L2 if you have an algorithm or a deterministic Turing machine such that for every W1 in the alphabet of L1, you can transform it in polynomial time to a W2 in the alphabet of L2 in such a way that this property is met. This property here. If W1 is gonna be in the language of L1, if and only if W2 is in the language of L2. Okay? So basically...
Teacher, the W is an input alphabet or what?
No, it's a W in the alphabet of L1. It's a string. Okay? It's a string. So basically it's saying this string belongs to the language L1 if and only if the transformation W2 belongs to the language of L2. So basically, what is sorry. Sorry, so it's basically telling me that I can reduce L1 to L2 in polynomial time. So every input that is supposed to be for L1 is transformed into an input for W2 for L2 in such a way that this property is met. We're going to see some examples, but the idea is that you are transforming one problem into another. Okay? But that transformation needs to be, we're going to discuss why, polynomial. So I'm going to show you this idea. One can show that the SAT problem, remember what SAT problem was? Anyone? Santiago?
Yeah, satisfactory.
Santiago Melo.
Es ese problema de las expresiones, o sea, que tengo las fórmulas y tengo que calcular si es satisfacible.
Exactly. You need to decide if it can be satisfied. So this problem can be reduced in polynomial time to 3 SAT. Do you remember what 3 SAT was? Someone else?
It's a variation of SAT where we have clauses of 3 literals.
Exactly. So the idea is, we illustrate this in a simple way. So we're gonna, for example, this expression here, this disjunction have 4 literal, right? x1, x2, x3, and x4. And there is a way to reduce this formula into another formula that uses only 3 variables or 3 literals. So look at this. You transform this E1 into E2 this way. So you have x1 or x2 or x3 or x4 is equivalent in terms of satisfiability to x1 or x2 or z and x3, x4, or the negation of z. I want you to take a pause there and try to think why these two things are the same in terms of each one being satisfiable.
And because because in both expressions, it's only necessary to be true one of the edges to be.
So remember that basically, I think it's true, but probably you mentioned only one direction.
Also, they are equivalent.
Yeah, so that's what we're gonna try to see. So you need to show that E1 is satisfiable if and only if, or let's write it with double implication, E2 is satisfiable. So first question, if E1 is satisfiable, then E2 is also satisfiable. Why?
And because they are equivalent. If all is one of the edges are true, the expression is true. If all the edges are false, the E2 is also false because the new variable set can be true on the left and true on the right because it's the negation. So can be true on both sides.
Okay, and the other direction, if yeah, somebody's saying something. Wait, Sebastián, tell us.
Preguntica. En este caso, en el de E2, ¿cierto?
Ujú.
Para la satisfabilidad del 2,
Mhm.
no tendría que darse en el que, por ejemplo, tanto el de la izquierda como el de la derecha sean 1.
That's true. Yes,
Entonces
that
ahí
is
por
correct.
ejemplo, ahí por ejemplo habría como, no sé, o yo lo veo como una diferencia con el de arriba,
Mhm.
porque no necesariamente uno solo tiene que ser el que esté en uno, por decirlo de alguna manera, sino que ya la condición tiene que estarse como con el 1 con el 1 y el 3 o el 1 y el 4 así.
Yeah, that is the problem, and this is why this part is critical. This is very important that you put Z, and here you put the negation of Z. And let's try to slow down there. For E1, let's assume that E1 can be satisfied. Then we know that one of these is 1, right? Do we agree on that?
Okay.
Wait. I'm gonna lead you to the answer. Now, you're right. To prove that E2 is then can then be satisfied, because if one can be satisfied, you need to prove that this one is true. I mean, that this one is satisfiable and that this one is also satisfiable.
Okay. O sea, en ese caso, por ejemplo, si yo no enciendo, pues viéndolo como una máquina, por ejemplo, si no enciendo ni X1, ni X2, ni X3, ni X4, como el valor de verdad recaería sobre Z y el complemento de Z.
Exacto.
Cualquiera de los dos en este caso podría dar 0, por tanto, entonces eso no se satisface. Pero si yo enciendo alguno de los dos, y por ejemplo, si enciendo X1 y pongo Z como 0, entonces en su complemento ahí estaría el 1 y 1 y 1 quedaría el 1.
Exactly. That's how it works.
Okay.
Interesting, right? So that means that you can reduce your problem with, I mean, doesn't matter how many literals you have, how many variables you have, you can always reduce it to 3. I illustrated here 4, but you can do the same from 5 to 4, and then from 4 to 3. Okay, and now this is this part here. Okay, so this formula is in SAT if and only if this formula is in 3 SAT, and that you have argued that is the case. You also need to prove that your transformation, this transformation can be done in polynomial time. So you need to argue about that. Can someone tell me why that's trivial? That you can write an algorithm that transform this into this in polynomial time.
Yeah, it's trivial because we only have to add like the set and the extra symbols and our linear time of extra symbols.
Okay, excellent. So now with these two things, basically it's telling me that 3 SAT is as hard as SAT, because every problem and that's the beauty of it, that every SAT problem can be reduced to a 3 SAT problem. That means that this guy here, this problem here, is as difficult as this guy here. That's something that you should keep in mind. Okay. Here's now. Wait, this definition. Yeah. Just another example is how to reduce. We already proved that SAT can be reduced to 3 SAT. And it turns out that 3 SAT can be reduced to click in polynomial time. That means that SAT itself can be reduced to click, because what you do is you first reduce, you go from SAT, then you reduce in polynomial time to 3 SAT, and then you go in polynomial time to click. That means that because you can compose these two reductions and get a polynomial time reduction from SAT to click. If this is polynomial and this is polynomial, why this one from here to here is polynomial? Can someone tell me?
Why the reduction from SAT to click is polynomial?
Yes, I'm going to show this, but I'm assuming that this one is polynomial, this one is polynomial. The question is, why this gives me a polynomial time reduction from sat to click?
Maybe because we are assuming like polynomials, a finite amount of polynomials, and that it's a polynomial.
Exactly. So because the sum of polynomials is a polynomial, right?
But when are finite polynomial.
Yeah, and there will be only finite problems. Okay. So that's clear. Now we're going to see how we reduce 3 sec to click. Let's erase this so you see it. The reduction is quite simple, and I just going to show some of them here. So suppose that you have your formula is like in this form, right? It should be in this form because we require this form, in particular conjunctive normal form. So each one of these is a clause. It's a clause and it's a clause, right? So you make as many groups as clauses you have. Okay, now once you have, in this case, 3 groups, group 1, group 2, group 3, group 4, now you're going to link the literals across the groups as follows. You are going to make an edge from a literal to another if those literals are not contradictory or complementary. For example, x2 and x1, they are not contradicting or complementary, so I just make this link here. X1 and the negation of x1 are contradictory, so I do not make a link. So from this group. So that means that I can make also this link here and this link here and so on and so forth. So you make all the possible links.
Teacher,
So,
why we can connect x2 and in the group 2 we have the x2, but why we connected in the with I can see it. Why can why we can connect it with its negation of s3 in the group 1?
why I'm not connecting this one with this one?
Yes.
Because if I make all connections, the graph is gonna look really weird. I'm gonna get tired. I mean, so that's what I say. I'm only illustrating some of them. Okay. Yes. So your question is, should I have a link from here to here? And the answer is yes. Yes.
Profe, una pregunta, digamos, en el grupo 4 hay un X2, ¿cierto?
Yes.
Pero ya en el grupo 2 como que con el X1 lo cogió, ¿cierto? Entonces también tendría que coger el del grupo 4, ¿o no?
Yes. You put
Ok.
in all
Sí, como
possible groups, you
todos los
connect them.
posibles grupos. Ok.
Yes,
Okay.
exactly.
Vale.
So basically, like the idea is that these guys are independent. Okay.
Profe, por el chat están preguntando que si la conexión hacia sí mismo es redundante, o sea, ¿por qué no aparece la conexión hacia sí mismo?
No, because I'm not making all connections. Okay. The only connections that are not possible are the ones in the what you may call it, the ones that are complementary. Okay. So just if that's not clear. For each vertex in a group, we put an edge to all vertices of the other groups, unless the two associated literals are complements. Okay, so then basically, remember the idea is to be able to, I'll explain why you can connect these two. For example, you want these two, right? That's what you want? To whoever asked, who asked that question? Yeah. So the idea is that basically you can make this group true by putting on 1 here. And if you put a 1 here, then you can go here and put a 1 here if you want. I mean, these two are kind of not contradictory. The same here. For these two are different. So you put 1 here, then this will be also sent to 1. So this will be true, and this will be true, for example, because they are not negated. Take it, for example, the negation of x1. This one. If you put this to false, then this will be, if x1 is false, this will be true, right? And then this also will be true, the negation of x1. So the idea is to be able to put one of these to 1. Now, if you can find a clique of size 4 here, this formula will be satisfiable. Can you see that? Can you see why? Can somebody explain why? Is someone talking or you are guys thinking? Nicolás Delgado.
Dígame.
Why do you think if you find a clique of size 4 here, this formula will be satisfiable?
Lo estoy pensando.
Okay. Just look. Try to find one.
No, por favor, a mí no me ocurre un motivo.
Okay, so here there is one. Wait. Give me a sec. This one, give you a click. Remember, Elkin, can you remind us what a click of size 1, 2, 3, 4 is?
Click de tamaño 4 es camino simple. Es un camino simple que usa todos los nodos, que usa todos los vértices del grafo.
Maybe.
No, that would be, I think you're confused with Hamiltonian acid.
Yes.
Sería.
No, sí. Un click, ya mejor decir. Un click es un subgrafo del grafo que tal que es completo.
Exactly. And of size k in this case, is size 4 in this case. So if we take this subgraph, look. So the whole graph here is like, well, 1, 2, 3, 4, 5, 6, 7, 8, 9. 12, right? And now we have selected a group of 4 nodes. And then I just need to verify that there is a path between each two. Here, 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 here. So it is a clique. It's a subset of this that is a complete graph, right? And now look at that and tell me that the existence of that clique, it means that the whole formula can be satisfied.
Porque para que sea completo tienen que estar un nodo en cada grupo diferente.
Yes, and you need to and. That's good, by the way. And what else? Because
also
wait,
if we have.
Let me compliment. Who was the one who talked before? Who gave this name?
Yo, Juan David.
Juan David, that was very good. And the reason for that is that, remember that we do not have links within groups. There is no link inside a group. So if there is a clique of size 4, it must be, it must involve all the groups, which was the thing that you said. Okay, and then now you just need to add a little idea, which I think that's what Rangif was going to say.
Sería
yeah, because we can have we can have like contradictory vertices.
Exactly. Since these are basically not contradictory, then basically you can go and say this must be 1, this must be 1. That means that x2 must be 0. This must be 1, and this must be 1, and then you get your assignment. Did you understand this?
Sería porque ese subgrafo que tenemos marcado puedo acceder a todos los grupos de un solo paso.
I don't know un solo paso would mean there.
Bueno, que digo, para que desde un grupo, de un nodo de cada grupo, puedo acceder a cualquier otro nodo de todos los grupos con un solo enlace, no hay enlaces de por medio.
Well, but it is a click. So it is a click. I mean, this is a click already. So that's included. What you just said is including the definition that this guy here is a click. The question was more why the existence of this click implied that this formula is satisfiable. And the reason is the way this graph is created means that there are no links within a group. So if there is a clique of size 4, there must be one edge in each group. There cannot be more than one edge per group, right? That's clear. And now, because these are independent, basically they are not contradictory, then you can assign each one of these to 1, true. And then this whole clause will be, which is this one, will be true. This clause here, this will be true. This clause here will be true, and this clause will also be true. Is that clear? Juan David is clear now? Does this... Juan David Gómez?
Claro, ¿me escuchan?
Yeah. No.
Sí, es que escuché el último muy entrecortado.
So you cannot hear me very well, or it's only him? How about the others?
No, es como que mi internet, por pedacitos.
Okay, so basically...
La noción está clara.
Okay, so that will be the reduction.
Profe, una duda. ¿No debería marcar también la línea horizontal doble que falta en el grafo? Porque No se pueden acceder a todo, porque el clic debe ser total y pues no están unidos todos los vértices. O sea, el vértice a la derecha no está conectado directamente con el de la
You
izquierda.
mean this one?
Sí, ese.
Yes, you're right. I missed that one. Okay. So we have proved that you can reduce all these problems in polynomial time. Okay. Now we can talk about NP completeness. Let me. A language is said to be NP complete if is NP. It can be decided in polynomial non-deterministic time, and every possible language L1 that is also in NP can be reduced in polynomial time to L. Let me write that down.
For example, set. No. Three set, sorry.
I'm going to erase this part here. So basically, putting it closer, what I have just said is the following. This problem A is NP complete if, of course, it needs to be NP. And for every other NP problem, you need to be able to reduce that problem into A in polynomial time. The first condition is very simple, right? I mean, it's just to find a polynomial time non-deterministic algorithm. And you know how to do that. You just guess and verify. Guess and verify. Okay? So, can you see the problem with this one? Anyone?
The problem with that?
Yeah. To
it's
check
like,
that one.
Okay, it's like I have to, in a way, check if all the NP problems can be reduced to A.
Yeah, and there are infinitely many. So, I mean, you can make up problems and prove that they are NP, right? Can imagine that. But luckily, he is the main thing. Let me go back. Oops, here. Okay. Let's suppose that instead of condition 2, we have this condition, I don't know what I call it, 2 prime, it's better to call it 3. And that means that 3 implies 2. This is going to be hard in general. So instead of doing that, you prove this one. You choose an NP complete problem B prime, and you reduce that problem in polynomial time to A. Well, I don't need to do all NP complete problems. I just need one. If I do this, I have this. That means if this property is satisfied, that implies that the second property is also satisfied. So I can just check these two conditions. Now, can you tell me why is I mean, This is a consequence of the definition of NP complete. Why is that? Sorry? Somebody say something?
Pues yo pensé que de pronto el tercero se cumplía porque si decimos que... No. Estaba pensando otra cosa.
Okay.
Iba a decir,
Okay, but what I'm saying is that this is an easy consequence of the definition. I mean that you can have that if you have these two things, then you have these two things. Can you tell me why? Meaning that condition 3 implies
Teacher, I know getting something. What means the transition between B to A, and what means
that B can be transformed in polynomial time to A. What we just saw in the previous, I mean, before.
Okay.
Okay, like for example, this could be SAT, and this could be 3 SAT.
Okay.
But what I need somebody to tell me is why, if you
I think that
Mhm.
they are like logical equivalent. Or like it's a negation of a for all, but I have a negation. No, wait.
No. Here you have NP and you have here NP complete.
Pero, profe, ¿y cómo, o sea, el NP completo son todos los NP, ¿cierto? O sea, todos los NP tales que, bueno, lo que no se entiende muy bien es, o sea, que usa la misma definición para esa tercera condición.
Yes, very good point. Very good point. But still is gonna be okay. But let's wait. Before that, let's suppose, Elkin, that you manage in such a way to find that SAT is NP complete. Suppose that you are given that. And now you want to prove that 3 SAT is also NP complete. So the first condition is easy to prove. You just given a random assignment to the three literals, and then you verify that can be done in polynomial time. The second is gonna be hard. You need to find all NP complete problems, like click all of them, and you need to reduce them in polynomial time to 3 SAT. That's hard, but if you only have to prove number 3 that says like, okay, it's enough if you prove that SAT can be reduced in polynomial time to 3 SAT. Why this would imply this? In another way, in other words, if you have this, how can you use this to prove this? How can you use 3 to prove 0.2?
Teacher, is there there is some relation between B and B comma?
No relation at all. It's just
There are two problems. Difference. Nothing in common.
No, not in common.
Maybe because if I'm already saying that B prime belongs to the set of NP complete problems, then it was already reduced by a set of NP problems, by a whole set of NP problems.
Exactly. So that's how you prove it. So basically, you are saying, okay, I have this. I'm gonna make a pic. I'm gonna do a drawing here, which probably I had before. So you need to, let's see that you have all NP here, and you need to prove that all these NP problems can be reduced in polynomial time to A, right? So you need to prove that this, and that's hard. But you know that SAT can be reduced to A in polynomial time. Then what you need to do to prove that this problem here can be reduced also in polynomial time to A? How can you do it? Just directly. I mean, just like easily. This one is NP complete. That's the trick. Because this one is NP complete, that means that they all can be reduced to this, right? So all of them in polynomial time, all of them in polynomial time. So how can you go?
So all of them can be reduced to A.
Exactly, because you just reduce this one to SAT, and then from SAT to A. So you do this like, this is a polynomial, this is another polynomial. That means that you can reduce this in polynomial time. You first transform it to this one, and then transform it to this one. You understand?
But
yes, I get it.
But we are given that a SAT problem is NP complete.
Yes, exactly. And
okay.
and I explain that later. But what I want you to appreciate here is the importance of NP complete problems, because whenever you want to prove, there is a list, I don't know, 100, 200 NP complete problems on the internet, and they're important because all the others can be reduced to them. That means whenever you come up with a new NP complete problem, you are giving tools to other people to find new NP complete problems, because they all can reduce to each other. So that's the importance. And now look, this is not the only importance. Now suppose that A is NP complete or SAT, and then you find a polynomial time solution for this guy. Wow, that means that they all have polynomial, deterministic polynomial time solution, because you can just reduce, and then solve this. So that's the importance of all these things. Yeah, what was the question?
Beautiful. How about the first NP complete problem? How they knew that it was NP complete?
Yeah. That's an interesting question. So the SAT problem is NP complete. And the idea, I mean, the details are really terrible. The idea is that you can take a Turing machine that find assignments to this formula, and the idea is that you can come up with a formula that can be satisfied if and only if that Turing machine goes into acceptance. And then you can prove that this sequence is polynomial. I mean, the number of configurations is polynomial. Then that way you can prove that this one is polynomial too. So this is the only one that basically you need to prove, not using this thing that I told you. For those ones that are interested in this complicated proof, I mean, you can find them on the internet very easily. And then they will explain how every move in a Turing machine can be translated into a formula in a conjunctive normal form. Okay, so that you do that way. So
Teacher, I didn't get it. What is the NP complete problems at the end?
At the end, an NP complete problem is any problem that satisfies these two conditions. Okay? So, but these two conditions are usually difficult to prove. Then you do it reducing another NP complete problem to it in polynomial time. And because you do this, then the second condition is met really easily by doing this. You need to prove that every NP problem can be reduced in polynomial time to A. But that's normally hard. It helps to know that SAT is actually NP complete. So you reduce SAT to A, then you found a way to reduce all of them to A by taking first the reduction from this one to SAT. Now, can you tell me, I'm assuming that SAT is NP complete, why is that I have these reductions here? Can someone tell me? Elkin?
For the
Assuming the what?
The SAT, sorry.
Sí.
Can you tell me, it's to explain to Alexander, why is that this works?
¿Me puede repetir la pregunta, por favor?
So the question was, I need to prove that every NP problem can be reduced in polynomial time to A. That's the condition 2, to prove that a problem is NP complete. Condition 2 requires this. And but I can do it using condition 3 instead, because that one implies this, and that's what I want to illustrate here. So condition 2 will require that every NP complete problem is reduced to this A. Why is enough just to prove that SAT can be reduced in polynomial time to A?
Porque si sabemos que SAT ya es NP complete, entonces todos los problemas NP se pueden reducir a SAT. Y entonces para probar que todos se pueden, si yo sé que desde SAT puedo reducir a A, o sea, en tiempo polinomial, entonces de todos los problemas NP también se pueden reducir a A en tiempo polinomial.
Because this from here to here takes polynomial time, this reduction. And from here to here it takes polynomial time. I mean, this is what you need to prove. The sum of two polynomials is a polynomial. So that means that this can be reduced doing this transformation and this other transformation also in polynomial time. Is that clear, Alexander? Alexander.
Entonces, un problema no polinomial completo, un problema NP completo es un problema que se deriva de otro no completo.
Not necessarily, because SAT, for example, I don't need to do that. It's just that the definition is this one, but if you do this, then you also have number 2. This work because I already knew that SAT is NP complete. Okay.
Profe, una preguntita. Entonces, ahí lo que estamos generando es como un punto de convergencia para todos esos problemas en B.
Exactly. Yes. That is the case.
Mi
So,
pregunta es, ¿cómo se puede, o sea, cómo llegamos, o sea, cómo generamos ese punto de convergencia?
You mean the SAT, for example?
Sí, señor, en ese caso, o sea, ¿cómo generaríamos ese punto de convergencia?
SAT is proven NP complete, these two, by using a complicated reduction, which I don't have the time to do it here, and I will have to introduce, I mean, this will require to follow a full course only in complexity theory. The proof of this consists on transforming Turing machines into formulas in conjunctive normal form in such a way that the formula can be satisfied if and only if that machine goes to an acceptance state. Okay.
Okay, o sea, lo que se hace es transformar todas las eh, todas las máquinas de Turing a fórmulas, y de allí lo que se busca es que por medio de eso el string que se entre sea igual o llegue al estado de aceptación tanto en la fórmula como en la máquina.
Exactly.
Okay.
So of course there is a relation between the size of the between the size of the formula and the Turing machine to be able to make sure that you have a polynomial non-deterministic time algorithm. But I mean, those are details that we are not going to cover in this course. Okay, so if I ask you to prove that some problem is NP complete, you can use a reduction from SAT, but now you know also that 3SAT is NP complete, right? So you can also use a reduction from 3SAT to it, or from the Hamiltonian path or click. They all are NP complete.
Nosotros podríamos ver ejemplo de cómo podría hacerse el proceso con algo un poco más específico para aterrizar un poco mejor la idea.
If you think about, we have done everything already here. First of all, how do we prove that a problem is NP complete? NP. Remember that part? We did for 3SAT, for example. Yeah, let's do it for 3SAT. So 3SAT is NP complete. Condition 1, show that 3SAT is NP. Can someone do that one?
¿Estás escribiendo, cierto, profe?
Yes, so sorry, you are not seeing what I'm writing?
I'm seeing it.
Yo no estoy viendo.
Okay, so sorry, Elkin, I guess it's a problem with your connection. So look, we are gonna, I think it was Nicolas who asked me to give an example, a concrete example. So we're gonna prove that, oops, sorry, I have a problem with my Apple Pen. Let me change something. Give me a sec. Okay, so we're gonna prove that 3SAT is NP complete. So condition number 1 is show that is NP. So we need to prove that this problem is NP. Can someone tell me how to do that?
We have to show that for solve that problem, we have to use the table truth. And the table truth takes exponential.
No. You're gonna prove that it's NP. Polynomial non-deterministic.
Lo que puede hacer es construir algo no determinístico, pero o lo que ya habíamos hecho era probado que SAT es no determinístico, es NP, y como de SAT se puede reducir a 3 SAT, pues no se probaría así. o no sé.
Well, basically, yes. Who said that? Elkin? No, what's that?
Sí, sí, fui yo.
Yeah, exactly. So this case in particular is very simple because 3SAT is a particular instance of SAT, and of course SAT is NP, but 3SAT is also NP. And the idea is, we saw it in the other class, you assign the three literals a Boolean variable, arbitrary Boolean variable, and then check if the formula under the substitution is, so let's take this example here, okay? Where is my, okay, so this is a particular instance, right? So this is the input to an algorithm, a non-deterministic algorithm. So what I do is I say, okay, I'm gonna assign each one of these three variables a Boolean value. So for example, x1 true, x2 true, and x3 false. I verify this. If the whole formula with those assignments is true, then I say it is satisfiable. If it's not, I don't say anything. So I guess, and then I verify. Do you remember that? That's what we did in the previous class with SAT.
Sí, es como solo seguir un camino, ¿cierto? Como solo seguir un camino del árbol.
Exactly, that's what it is. It's the easiest possible thing. You guess something and you verify. Why is that this can be done in polynomial time? Guessing is linear, right? You give x1 a value, x2 a variable, and x3 a variable. And verifying. Why is verifying that this formula with those assignments is true? Very simple.
Eso se podría ver como n por m.
What is n and what is?
N es el número de variables y m sería el tamaño.
Yes, in general, what you do is, I mean, yes, you could actually do that, but you don't want an m unless that m is a constant that is not related to n. Fine, but in that case, if m in the worst case is n, then it would be n squared, right? But how can you check if this formula under some assignment is satisfiable or not? You find the value of this formula with that assignment. How can you do that? In a very simple way.
You just evaluate and check if it is one.
Yeah, you just check the truth table. I mean, you just take you put this formula into Python and it will give you immediately the answer if you give the values of x1, x2, and x3. You see that or not?
Yes.
Yes.
Okay, so then you have proven that it's NP, right? It's NP. It can be solved non-deterministically in polynomial time. That means that you can verify in polynomial time. NP, whenever you do an exercise of this, remember, the first part is trivial. You just need to know how to verify polynomial time. The second part is the most difficult, but we do it for number 3, which is actually very difficult. So you need to reduce a known NP complete to it. But so how can you do that? We already did, but what NP complete problem you reduce to it?
SAT problem.
Yeah, so we already saw that SAT can be reduced in polynomial time to 3SAT. And that was not very difficult, right? Because we just added this extra set variable, remember or not? The reduction was just this one here. You add this set and not set. So Nicolás, is that clear now?
Creo que el que preguntó fue Reyes.
Reyes. Reyes.
Sí, ya es más claro.
You guys have similar voices. Okay. So, and then you can do the same with click, right? Let's do it with click. Okay, click. Oops. So I'm trying to write with my finger. It's harder. Okay, click. Okay, click. Yeah.
La reducción es bidireccional. La reducción, o sea, si puedo de un problema a otro, puedo de ese otro al problema.
I think that yes.
Yes.
Okay. Vale.
Yes, sure. Because it's every MP. That includes the MP completes already. Okay, so this one. K-click is MP complete. Why is K-click NP?
Because
How can you show it? We did already in the last class, but maybe.
yes, like we guess the subset and we check in linear time, in polynomial time.
Exactly. You take any subset and you check in polynomial time, there is an edge between every vertex in that subset. That can be done in the size of the subset, right? Which is always smaller than the size of the total number of vertices. So, Reyes, is that clear?
Sí, sí, señor.
So this one and now, what kind of reductions I use to prove?
We reducted 3 set and we show that 3 set is in NP complete. So K-click is complete, is NP complete.
Exactly. Since we proved that 3 sat is NP complete, and then we reduce also 3 sat to the K-click problem, then you prove that this one is NP complete, because we proved this third condition, which implies the second condition, so we are fine. So I gave you two examples of how to do this. So, and then when I give you an exercise to work on, basically you will have to find or to be able to figure out what's the NP complete problem you need to reduce to. Okay, is that clear?
Clear.
Okay, so if there are no more questions, I'll see you next Friday. Okay. Nicolás, nos vemos.
Okay.
Voy a parar la grabación.
Okay.